Well, we have question 9 here. The question says the graph of y equal to 9ax squared plus bx plus c below represents the derivative of f. So this is the graph of y that represents the derivative of f. Now it is given that f prime of 1 equal to 0, and then f prime of 3 equal to 0, and f prime of 0 equal to 6. Now in the previous video, we did work out question 9.1 and 9.2, as we can see here. Now we're going to do question 9.3 that says, explain which value of x, the stationary point, f will be the local minimum. All right, I'm going to do that with the help of question 9.2 because it's where I, in the previous video. So let me just split my code this way. In 9.2, I gave you an idea of how I get this graph right. Okay, let me do it over here. Maybe I should just draw the graph of f. So let's see, this is the back coordinates. Okay, and then I'm going to draw let's see the function state. Now from the graph here, I know that we in the previous question we found the stationary point, which was 1 and 3. So if 1 is somewhere here, 3 would be somewhere there. Okay, maybe let me, because of space, I'm going to do, let's say 1 is here, and then 3 is there, somewhere there. Okay. Now, if I look at this graph here, the graph of, the graph of the derivative of the function. Okay, that's the derivative of the function. Let me make it a little bit bigger. So, okay, this is the derivative of the function. It makes a U shape. By that, I understand that the function itself has a positive gradient. Okay, because it has a U shape, it means it has a positive gradient itself. The leading coefficient. That's what I wanted to say. A over here, the leading coefficient A is greater than 0, positive. Therefore, the leading coefficient of f of x also will be A will be also positive. It means if it's positive, it means the graph increases, decreases, increases again. So the graph would be go up, and down. Oh, what am I saying? Let me redraw it. The graph would be like this: up, down, round, up again. So this is the cubic function. Okay. So my graph will be doing something like this. So now if I need to draw a graph like this in this Cartesian plane, I understand that the turning point, it will have its maximum by 1 here. So it will have its maximum by 1 here, and then it will have its minimum here by 3. So the graph may look like, will look like something like that. So to look like something like this. So turning points over here, turning point over here. So it will come like this and go up there. Yes. Now, when the question 9.3 over here says that explain at which value of x the stationary point f will be a local minimum. Okay. Now I will see that we have a local minimum by x is equal to 3 because the turning point is over here. Okay, the local minimum, therefore I will say, therefore it is x is equal to 3. That's the value of it, because at x is equal to 1, we have a local maximum. So it's over here, x is equal to 3. Okay. Okay, now let's see the next question. And now we're doing question 9.4. Question 9.4. Question 9.4 says, determine the x coordinates of the point of inflection of f. Okay, the point of inflection of f right here. So 9.4. The point of inflection is where the derivative, where we need to find the second derivative of x. Okay, but the condition is when that second derivative of f equals to 0. So we're going to set f second, which is f derivatives prime f seconds of x is equal to 0. Now so when we look at okay, from the graph, let me paste it here. Oh, maybe I want to do as I was saying, the second derivative of we have the point of inflection when the second derivative is equal to 0. Now let me just place in the graph here of f prime. If f prime look like this, f prime is exactly at the turning point. Okay, this is where f prime is. Or in short, f second. The point of inflection is somewhere here at this point here. Now, yes, because if we differentiate the derivative of this equal to 0 here when the tangent line is makes an horizontal line. Okay, if you know the properties of cubic functions, so it is 0 at the maximum. In other words, to say. So this is the first derivative. We have it like that. We have it like this. But the first derivative is like that. And now the second derivative is 0 at the turning point. Okay. So over here we have f prime equal to 0 or f second equal to 0. Now we already know the values, this value and that value from the previous question. The previous video we see that we have 1 over here and 3 over there, the stationary point. Now, if I need to find the turning point, I can just work out the average of 1 and 3. So we can do the turning point or the point of inflection x here will be equal to x1 plus x2 all over 2. So which is x is equal to 1 plus 3 over 2. That's just a tablet, so that makes x is equal to 2. So the point of inflection is equal to 2. Now, question 9.5. We can do question 9.5. Let's see what question 9.5 says. We had question 9.5 that says for which values of x is f concave up? Concave up is when it turns like this. Okay. The concavity is found when the second derivative is greater than 0. So it's when, okay, right here 9.4. 9.5, I mean. Okay, we're looking for the value of x for which f concave up. So this is possible only when the second derivative of x is greater or equal to 0. This is the condition to have a concave up. Concave down will be lesser than 0. Point of inflection will be the second derivative equal to 0. Now, in this situation, let's first look at the graph again. The graph is like that. Okay, let me make it a little bit bigger. Oh, like that. Okay. Now we already have these points. We have Like from the previous question, we had this one was 1 and that one was 3. And then we have this point equal to 2. We have 2 here. Now, we said it's concave up if this condition, okay? By this condition, if the second derivative is greater than 0. No, but the second derivative is greater than 0 if x is more than 2. Because here, you see, here it goes down, but there it goes up. So this is possible only if x is greater or equal to 2. So this is the condition. Thank you.